Good morning, everyone. Hope you're all doing well and had a nice break there. I have been sort of chipping away at some emails, so if you haven't gotten a response to me, if you did send me one last week, you'll be getting it in the next day or so. So we left off, we had talked about chapter 6, we did chapter 7. Chapter 6 was all about like calculations. Chapter 7 was all about like balancing chemical equations and writing chemical equations. This chapter is going to combine those two things together. Currently, your third test, which I think tends to be the most challenging for students, so you may want to start studying now as opposed to like right before it. But that third test is going to be this Sunday. So just keep that in your mind somewhere. Okay, so let's go to chapter 8, quantities in chemical reactions. So we're going to look at chemical reactions. We're going to calculate actual quantitative or numerical values from different things. So global warming, too much carbon dioxide. Okay, the combustion of fossil fuels, such as octane. So octane is a component in gasoline. It will produce carbon dioxide and water. Hopefully you guys that remember that when we have a combustion reaction, we always get CO2 and H2O. Carbon dioxide is known as a greenhouse gas, meaning that it contributes to sort of this insulation quality of our atmosphere and increases temperatures. So light comes in from the sun. If the greenhouse gas layer is really thick, it's hard for the heat or the radiation from the sun to escape. So we sort of create this nice warm greenhouse effect. The same thing happens if you have a greenhouse in your backyard. It stays a little bit warmer than the surrounding temperature in winter. So here is the balanced chemical equation for octane. So there's octane. Again, I don't expect you to know nomenclature for organic stuff. So don't get freaked out if you're like, I don't know that's octane. I would give you the formula for it. So we have octane. Remember, if it's a combustion, it combines with oxygen. It produces CO2 and H2O, and when it's balanced, we get these coefficients. So 2 octanes combined with 25 oxygens, you get 16 CO2s and 18 waters. The thing with this is, remember when we were talking about looking at just specific formulas, like this formula here? This says that for every 1 mole of this octane, how many moles of carbon do we get? We get 8 moles of carbon, right? And we get 18 moles of the hydrogen, because these numbers here are not just an atom relationship, they're also a molar relationship. So they tell me how many moles of each I have in there. It's not a mass relationship. The same thing is true for a balanced chemical equation. These coefficients that are in front tell me a molecular, like how many molecules of each I have, but it's also a molar relationship. So I need 2 moles of this to combine with 25 moles of this, and I can produce 16 moles of this and 18 moles of this. So those coefficients, when the equation is balanced correctly, it's really cool. I can give you an amount of octane and you could actually calculate and tell me how much CO2 is produced, because there's a relationship there. 2 moles of this will always produce 16 moles of this if we're running this equation. Now those coefficients are unique to each equation. So the relationship is not always a 2 to 16 if it's something besides octane or something besides CO2, right? This is specific to this equation. Just like these numbers are specific to the formula of octane. So since we know, for the most part, the world's annual fossil fuel consumption, we know how much fossil fuel we use, we can estimate how much CO2 is actually being pumped out. We can calculate that by using this relationship. If I know how much of this stuff we've used, I can tell you how much of this stuff is getting produced. So if you ever wonder, well, how do they actually know how much CO2 is, getting pumped into the atmosphere? Like, are those numbers just made up? No, they know for a fact how much octane they've sold, because there's a lot of money in that. So they know gallon per gallon how much of this has been sold and used, so they can calculate how much of this has been created. So that process of going from like how much of a reactant to how much of a product you have is called stoichiometry. That's just a fancy way of saying the numerical relationship between chemical quantities in a balanced equation. So stoichiometry means you can go from a certain amount of reactant to a certain amount of product. You can also predict how much reactant you need if you want a given amount of product. Let's say for whatever weird reason, like I want to produce 15 grams of CO2. I could figure out, well, how much octane do I have to burn to get 15 grams of CO2, right? And then you can also go from one reactant to another reactant. You could even go from one product to another product. If I said, hey, we produce, 100 grams of CO2, well, how much water would get produced? Well, there's a relationship between 16 moles of this for every 18 moles of that. So stoichiometry and this process of going from one thing to another is very similar to baking. So we're going to use that analogy. So making pancakes. So here is a recipe for making pancakes. You can kind of think of this as a chemical reaction. We've got a couple things that we're starting with, and we have something that we're producing. And then there's these numbers that sit in the front, right? These are behaving like the coefficients in our chemical equation. So we don't just say, when you're making pancakes, you don't say, oh, I'm going to take flour plus egg plus baking powder and I'm going to make pancake, right? You have to have some sort of numerical value in the front to let the reader know, like, how much of each do I really need? Same thing is true with a balanced chemical equation. So let's go back here. We don't just say, hey, octane plus oxygen produces CO2 and water. We say, hey, 2 of these and 25 of these will produce a specific amount. So we've got our recipe for pancakes here: 1 cup of flour, 2 eggs, half a teaspoon of baking powder, and that will always yield 5 pancakes. So within this balanced equation, we have all these conversion factors. Each of these things relate to each other. If I have 1 cup of flour, how many pancakes can I produce? 5, right? If I have 2 eggs, how many pancakes can I produce? 5. Half a teaspoon of baking powder, 5 pancakes. So let's look at this here. We've got specifically looking at eggs. For every 2 eggs, I can make 5 pancakes. That's assuming that I have an excess amount of everything else, right? That, like, I have a huge bag of flour and more baking powder than I could need, or baking soda, whatever it is. So 2 eggs for 5 pancakes. So what if we had 8 eggs? And you're just trying to figure out, you have a bunch of friends over and you want to figure out how many pancakes you can possibly make. So if I have 8 eggs, I use this relationship here with the quote unquote coefficients, right? For every 2 eggs, I get 5 pancakes. And I'm going to situate it in such a way that the egg goes on the bottom and the pancake goes on top, right? So we have 8 eggs. We want to see how many pancakes we can get. Let's get rid of the eggs. We'll take the 8 times the 5 divided by 2. And we end up yielding 20 pancakes. And my guess is you could probably do that in your head, right? If you know 2 eggs produces 20 pancakes, or I'm sorry, 2 eggs produces 5 pancakes, well then 8 eggs, which is 4 times as much, should produce 20 pancakes. Same thing is happening when we're doing stoichiometry if we have a chemical equation. This conversion factor here is coming from the coefficients. So I want you to do one simple one with the baking. Okay, let's say that you're given that you have 13.2 cups of flour. And you have an excess amount of eggs and baking powder. So you don't even really have to worry about eggs or baking powder because we've got a bunch of them. I want to find how many pancakes could you make? So set it up in a dimensional analysis style, just so that when we go back to actual equations, your setup is already there for you. Okay, so with this, we're given something about flour and we want to find something about pancakes. Because the problem says everything else is in excess, just ignore this stuff. It's not that it isn't important. I mean, you need it in order to balance the recipe, right? But we just have more than enough of it. So we only need to look at the relationship between flour and pancakes. And in this case, it says 1 cup of the flour will yield 5 pancakes, right? If we start with 13.2 cups of flour, well, I'm going to use this. I'm going to use this conversion factor, and I want to put the flour on the bottom, right? 1 cup of flour on the bottom for 5 pancakes. So I take my original number and I'm just going to multiply it by 5 in this case. I end up getting 66 pancakes. This is an exact ratio, so we really want to have 3 sig figs because this has 3 sig figs. So I'm going to say it's actually 66.0, just to give it 3 sig figs. Again, my anal retentiveness for sig figs starts to drop off pretty dramatically here, but just to be a stickler, we'll go with 66.0. So if you've done any baking in your life, this is not revolutionary, right? This is how you read a recipe. Well, the same thing is going on with a chemical formula. Think about this as a recipe. Now, this recipe, though, is a mole-to-mole recipe, okay? It's not a mass recipe. It's not saying, like if we look at this one here, for instance, this is the synthesis of ammonia. We are not saying 3 grams of this and 1 gram of this produces 2 grams of this. We're saying 3 moles of this combines with 1 mole of this to produce 2 moles of this. Those coefficients in the front become our conversion factors. So some of the relationships that we have here are 3 moles of H2. Well, these are writing it as molecule. Molecule and mole are equivalent, really. So 3 moles of the hydrogen gas needs 1 mole of nitrogen. 3 moles of the hydrogen gas produces 2 moles of ammonia. 2 moles of ammonia need 1 mole of nitrogen diatomic to produce it. So all these things are built into the equation. I can use any one of them. I could use this thing. I could use the relationship of this with this. Or depending on what the problem's asking, I could relate this thing to this thing. It's a 1 to 3. Or, you know, I've also got this to this. This is a 1 to 2 ratio. So it's all in there for you. So I'm going to give you an equation and I want you to tell me all the possible conversion factors that are available to it. Let's do, we'll do the synthesis of aluminum oxide. So aluminum combines with oxygen to produce aluminum oxide, which is Al2O3. Now I'm going to want to balance this thing. So I'm going to put a 2 here. I'm going to put a 3 here, and I'm going to put a 4 here. Okay, so this is balanced for you. So I want you to write 3 different conversion factors. 1, 2, 3. There's 3 possible things that you can combine together, mole relationships. I'll give you all, shouldn't take you more than a minute or so. Okay, so The first one that I'm going to relate aluminum to the product. And just because this has aluminum in it, it's not the same thing. Okay, this is aluminum by itself. This is aluminum oxide, a compound. Sometimes I get students mixing those up. So if the problem is saying how much aluminum, it's not talking about this thing, it's talking about this thing over here. So 4 moles of aluminum, 4 moles of the aluminum will produce or can yield 2 moles of my aluminum oxide. All right, 4-to-2 ratio. That's one relationship. Another relationship is my relationship between the oxygen and the product. So 3 moles of oxygen, but oxygen is O2, okay? If it's by itself like this, and it is a diatomic, make sure you 2 it up. So 3 moles of aluminum, 3 moles of oxygen will produce 2 moles of the aluminum oxide, right? Built into for you right there. The last one, I'm just going to relate the 2 reactants. 4 moles of aluminum will need to react with 3 moles of the oxygen. Okay? There's no other ones in there that we can't get. So all these different conversion factors built in. Which one do you use? It's really dependent on what the problem is asking. So let's go back to the slides, and then we will do an example with this one. So keep that close. So we've got our ammonium, the synthesis of ammonia. And this problem here, it says, hey, if we have 3 moles of the nitrogen and more than enough hydrogen, so when it says more than enough hydrogen, you can sort of just ignore the hydrogen. So it's like, bye, leave you alone. We know something about this. It says, how much of the product can we make? How much of this can we make? So we want to hop from nitrogen to the ammonia product. Well, what is the relationship between those two things? 1 mole of this will always produce 2 moles of this, right? And that's what we have right here. 1 mole of the nitrogen produces 2 moles of the ammonia. If we have 3 moles of the ammonia, that's our given information. That's what we're going to start with. There's our 3 moles. We just need to make sure that we make this conversion factor set up so that it cancels what we don't want. It's the same as all of our conversion factor, all of our dimensional analysis this entire semester. You're just going from one thing into another thing. So we put the nitrogen on the bottom, specifically the 1 mole, and we have 2 moles of the product on top, and we get 6 moles of the product. Okay. Any questions on that setup or where those numbers are coming from? This 2 is coming from this 2. This 1 is coming from the inferred one that's in front there. So I'm going to have you work through one using that last thing we had. So let's say that we're given that we have 9.73 moles of oxygen. I want you to find moles of the product, Al2O3. Okay. So your given is that there is 9.73 moles of oxygen. How many moles of aluminum oxide will you produce? So pick out which conversion factor you like that makes sense to use, set it up in dimensional analysis, and then solve. I'll give you 2 minutes for that. Okay, so in this hypothetical problem here, you're given a certain amount of oxygen. So I'm just going to even underline it in the problem or the equation. And we want to figure out the amount of aluminum oxide. So I want to relate oxygen to aluminum oxide. So of these three relationships, this is the one that makes sense for us to use. We don't care about aluminum on its own, so we don't need those two. As you get better at these, you don't need to write all of the relationships. You can just look at the original equation and see, hey, this is a 3-to-2 relationship. I just was laying it out so that we could make sure we knew where everything was coming from. So we start with our given information. We have 9.37, nope, we've got 9.73 moles of the oxygen. And we want to get into moles of O2 or Al2O3, moles of Al2O3. All right, that's my desired unit. My unit that I want to get rid of is that mole of O2. So then I just put in the correct coefficients. Well, this is a 3-to-2 ratio. So 3 moles of O2 will yield 2 moles of that Al2O3. And these will cancel. And then you just plug it into your calculator, as simple as multiplying the stuff on the top. So the 9.73 times 2. And then we don't forget to divide it by anything that's on the bottom. So we divide it by the 3. And it says that we end up with 6.49 moles of the Al2O3. And I could do that with any sort of relationship. So instead of giving you something about O2, I could have said, I could give you something about, let's just do it. Give you that we have 1.32 moles of aluminum. And I want you to find how much oxygen you need to combine with that, right? And in that instance, we're looking at aluminum and oxygen. It's a 4-to-3 ratio. So we just set it up a very similar way, 1.32 moles of aluminum. I'm going to put the mole of aluminum on the bottom. I'm going to put what I want, the mole of oxygen, on top. And then I figure out their relationship, which we said was a 4-to-3 relationship. Multiply everything on the top and divide anything that's on the bottom. So the 1.32 times 3, and then we divide it by 4. We get 0.99. So 0.99, I'll give it a 0 moles of the O2. Any questions on where those numbers are coming from on that system and how we're doing that? If you do, you can just turn your mute off and ask me. Hopefully it feels sort of simple. We're going to add some stuff to it, always. Key here being, what have we done thus far? Everything we have done thus far has been a mole to mole transition, right? You've been given information. Your given information is in moles. What you're trying to find is in moles. So going back to the slides, this is talking about the Clean Water Act. So how often is information given to you in moles? And how often do you want it in moles, like in real life? Not very often. Usually you're given information in grams or a mass value and you want it in a mass value. So this is going to be sort of your general flow chart for stoichiometry. A is talking about compound A, your given information. Okay, so this is given. This is what you're trying to find. That's compound B. We've already done this step here, this inner step, going from moles of A to moles of B. How do we do that? We use the ratios from the balanced equation. So that one's already done. But again, we're not usually given things in moles. We're given things in grams or mass. Going from a mass to mole is pretty easy. If you remember, you just use the molar mass, right? So if I want to go from grams or mass of A into moles of A, I use the molar mass of whatever compound A is. On the tail end, if I've hopped over to moles of B and I want to get grams of B, I'm going to use the molar mass of B. So it's always this flow chart of grams into moles into grams, or grams of A into moles of A into moles of B into grams of B. We've practiced this middle step pretty well, hopefully. These first part and this last part you did from chapter 6. All right, that was just the formula molar mass, but we're gonna do it anyway. So let's, I don't like this problem. I don't want to do that one. I'll make one up. Okay, so why don't we keep going with this formula here? I'm going to erase some of this stuff though. Not erase that much. You know what? We're just going to clear it all out. So we had aluminum plus oxygen produces aluminum oxide. 2, 3, 4. So let's shift our problem, make it a little more challenging and say, hey, how many grams of Al2O3 are produced from, where did that 4 come from? From 6.75 grams of aluminum and endless oxygen. So anytime you see things that say endless or excess or abundance, it means that we don't have to really worry about this. Okay, so we have more than enough oxygen, so I'm not really going to think about that. I'm given an amount of aluminum in grams. I want to figure out the amount of aluminum oxide in grams. So the flow chart for this is grams of A into moles of A. Sorry, moles of A into moles of B into grams of B. When I say A and B, A again is our starting thing. So this is my A. Aluminum is the A, starting compound. B is the aluminum oxide. So let's make this even more specific. We're going to want grams of aluminum. We're going to want to convert that into moles of aluminum. Then we're going to want to convert it into moles of the product, Al2O3. And we're going to want to convert it into grams of the product, Al2O3. Box this up a little bit. So there's 2 extra steps here, right? It's the molar mass of aluminum to get us here, and it's the molar mass of aluminum oxide. The molar mass of aluminum, this thing here is 1 mole of aluminum weighs 26.98 grams aluminum, right? This middle step, this is the coefficients. Well, 4 moles of the aluminum will always produce 2 moles of the aluminum oxide. And then this step over here, we need the molar mass of aluminum oxide, which is something heavy. Al2O3, what do we got? 101.96 grams for every 1 mole. You guys seeing where all those steps are coming from? The intermittent steps, what are our conversion factors? Yes, no, maybe so. Okay. So this is, how many hops are we taking here? We're taking 1 hop, 2 hops, 3 hops, 3 hops. I'm going to just chain all of mine together. Again, you can't always stop and start back up, but I like to stick mine all together. So we start with our given information, which is 6.75 grams of aluminum. What is my first step on the flow chart? It's to go from grams of aluminum into moles of aluminum. So I want to get rid of grams of aluminum and I want to get into moles of aluminum. Well, this tells me 1 mole of aluminum is 26.98 grams. Only use the coefficients on this middle step. Sometimes what students will do is they'll say, well, I don't have 1 mole of aluminum. I have 4 moles of aluminum. Well, this first step is just converting using molar mass. We use the relationship with 1. The 4 comes into play in the middle step. So now I want to do my magic hop, which is where I need the balanced equation that says, hey, I'm going from moles of aluminum into moles of aluminum oxide. So 1 mole of aluminum, 4 moles of aluminum, 4 moles of aluminum will yield 2 moles of aluminum oxide. The last step is, so we've hopped here, the last step is to hop into our final gram value of aluminum oxide. Well, 1 mole of aluminum oxide will always weigh 101.96 grams of the Al2O3. You want to check and make sure everything cancels, right? So here is grams of aluminum, our starting thing. It is canceling with the gram of aluminum. Here's mole of aluminum. It's canceling with mole of aluminum. Here's mole of the aluminum oxide or the product. It's canceling with mole of the aluminum oxide. And what is the only unit that remains? Gram of aluminum oxide. So now we have to plug this into our calculator. You've got to multiply across the top, divide by anything on the bottom. So 6.75, we're going to multiply it by a 2 and that 101.96. And then I've got a couple things to divide it by. I've got to divide it by 26.98. And then I also have to divide it by 4. And what I end up getting is 12 point, I need 3 sig figs, so 12.8 grams of Al2O3. So it doesn't matter what stoichiometry problem you're given, this is the flow chart you're gonna follow. If we aren't given grams, we're given moles, we can just sort of like truncate off these sides. That's what we did in the very beginning when we were going from moles of one thing to moles of another. Usually though, you're going to be given things in grams. So I'm going to give you another problem and I want you to calculate the stoichiometry. Now, one thing students ask is, well, how do I know I need to even do stoichiometry? If you're given a balanced equation, if it's giving you information about one compound and it wants you to tell it about information on another compound, you're probably doing stoichiometry. So let's do this one. How many grams of oxygen are needed to produce 83.6 grams of CO2 given the following equation. C3H8 plus O2 produces CO2 plus H2O. Let me balance it. I'll balance it for y'all. So 3, 8, 4, 6, 10, 5. Okay. So here is your balanced equation. You're not always given a balanced equation. Sometimes you have to balance it. So just check, make sure it's balanced. If there's coefficients, it's balanced. I'm not going to like give you coefficients and have it balanced incorrectly. I won't be that evil. But check and make sure it's balanced. So how many grams of oxygen are needed to produce 83.6 grams of CO2 given the following equation? All right, so you're given grams about one thing, CO2. It's asking about grams of another thing, O2, and there's a balanced equation. You're probably going to want to do stoichiometry. So I'm going to give you all 4 minutes to work through that. Setup is very similar to the last one, grams to moles to grams, but obviously it's a different problem in a different equation. So looking at this one here, I'm going to write the flow chart out. We're given information about CO2 in grams. So I'm going to go from grams of CO2 into moles of CO2, moles of CO2 into moles of oxygen, and then moles of oxygen into grams of oxygen. That should be your sort of your thought process with this. Start with my given information, which is this here. So 83.6 grams of CO2. And I want to go into moles of CO2. Well, I need the molar mass of CO2, which is 40, like roughly 44. So 1 mole of CO2 should weigh roughly 44, it's like 44.01 or something grams of CO2. The next step is to go from moles of CO2 into moles of oxygen. That middle step is where we use the coefficients. So 3 moles of CO2 will always produce 5 moles of oxygen. So let's go ahead and plug that in. I want the CO2 on the bottom. So 3 moles of CO2 on the bottom so that the CO2 goes away, and it will produce 5 moles of O2. The last step is to go from moles of O2 into grams of O2. The thing I want to note here is this is a diatomic molecule. So it's not presented as just oxygen. It's oxygen bonded to itself. So you need to use the molar mass of 2 oxygens. If it has a 2 there, you got to double up your oxygen. So 1 mole of O2 is not 16, it's actually 32 grams of oxygen. Okay, that is going to be the case when you have diatomics like that. So please make sure to take that into account. We're going to multiply across the top, 83.6 times 5 times 32, and then divide by anything on the bottom. So we've got 44. What else do we have? We have a 3, and then the 1 we don't need to worry about. So this is telling me that I can produce 101, or sorry, I need 101 grams of O2 to produce 83.6 grams of the CO2. So I can go from a product and figure out how much of the reactant I need as well. We have all different ways of hopping around. Are you seeing how this is really, setup wise, is identical to this problem? It's just a different balanced equation, and it's a different set of numbers, but the flow is the same. It's grams of your starting into moles of your starting, moles of your starting into moles of the ending thing, and then into grams at the ending. We're going to continue to do a bunch of more practice with this in another way. So we will keep doing this. I don't want to do any more in this setup, but when we get to limiting reactant, we will do it. So let's go to a couple things, a couple words that I want to expand on. So there's something known as a limiting reactant, a theoretical yield, and a percent yield. So a limiting reactant means that you have a very specific amount of 2 or more reactants, and one of them is holding the reaction back. A theoretical yield is, in theory, what could you produce? And then a percent yield is what you produce in real life, actually. So let's go back to the pancakes. Let's say we've got this. We've got our recipe. It's 1 cup of flour, 2 eggs, a half a teaspoon of baking powder, and that will yield 5 pancakes. So you go into your pantry and you find, okay, I've got 3 cups of flour, I've got 10 eggs, and I've got 4 teaspoons of baking powder. I want to know how many pancakes could I make? Well, this is sort of trying to compare like apples to oranges. So what I need to do is figure out, like, get everything into the same unit or the same product. So what I'm going to do is take each of these things and determine how many pancakes I could produce in theory. So if I have 3 cups of flour, using the relationship in the recipe, I could potentially produce 15 pancakes, right? If I have 10 eggs, I could produce 25 pancakes. And if I have 4 teaspoons of baking powder, I could produce 40 pancakes. So if you have a big party, you may be thinking, woohoo, I can make 40 pancakes. Actually, you can't. Why? Because the eggs and the flour are limiting how much you can produce, right? You don't have enough eggs to make 40 pancakes. You don't have enough flour to produce 40 pancakes. So instead, given these initial amounts, the number of complete and like appetizing pancakes I could produce are 15 pancakes. This is known as your theoretical yield. In theory, I could produce 15 pancakes. The flour is your limiting reactant. It is the reactant or the ingredient that is holding the reaction back. It's what's limiting how much you can produce. The eggs and the baking powder would be known as something called an excess reactant. You have more than what the limiting reactant can produce. Good with that so far as the baking ratio? Okay. So the theoretical yield is how much the limiting reactant produces. The limiting reactant is what ingredient is holding the recipe back. Now, if you've ever made pancakes, right, you always burn the first couple, like you never get them just right. So let's say that we burn 3 of them and then one falls on the floor and you're not going to eat that one. So even though in theory you could produce 15 pancakes, we are only actually producing 11 pancakes. If this were a chemical reaction, we could calculate something called the actual yield. The actual yield is like, how good are you at producing the product? In this case, how good are you at producing pancakes? You've lost 4 of them. So what is the equation for actual yield? It's this right here, or I'm sorry, the 11 pancakes is the actual yield. So that's what's happening in real life. Actual yield is something that you are going to get experimentally. Or it'll be given. Okay, on a test, I'd give you the actual yield because you're not going to run an experiment in your house while you're doing a take-home test. I was jumping ahead a little bit. Then we have this thing called percent yield. So percent yield is how good you are at actually making the pancakes. So for percent yield is always going to be A over T, actual over theoretical times 100. A comes before T in the alphabet, so put the actual on top and put the theoretical on the bottom. Multiply it by 100 to get it into percentage. So in this case, hey, I've got 15 pancakes in theory. I only produce 11. Take 11 divided by 15 and multiply it by 100, 73%. So since 4 of the pancakes were ruined, you only produce 73% of what the theoretical yield was. If you were working in a pancake shop and you were wasting, upwards of 27% of the pancake batter, you'd probably lose your job because that's quite a bit of ingredient to lose. So the actual yield of a chemical reaction will be determined experimentally, i.e. that'll usually be given to you. The actual yield is usually less than 100%. You don't usually produce more than the theoretical yield unless something funky happened with your calculations. Some of the product just doesn't form. Product is lost in the process of recovering it. You do expect there to be a small amount of difference in your percent yield. Like you're never 100%, but you probably wouldn't want to be 73%. So to summarize that, the limiting reactant is the reactant that holds the reaction back. The theoretical yield is the one that is the amount that you can produce based off of the limiting reactant. The actual yield is how much is actually produced, and the percent yield is the actual divided by theoretical times 100. So let's relate this to a calculation. I don't really like these slide problems because I think I remember one of them being they flip-flop something. So I'm going to use something from our slides here. So how that whole baking thing relates to stoichiometry. Let's do this first one because it doesn't have the answers, so we can go with it. Okay. So I've got this problem here. And it says, here's your equation. So it's a pretty dramatic equation, right? 2KAuCl4 plus 3Na2CO3 plus 3 H2Os produces 2AuOH3s plus 6 NaCls plus 2 KCls plus 3 CO2s. It says your starting substances are, you have 20 grams of the KAuCl4 and you have 25 grams of the Na2CO3. It says you're working towards AuOH3, and it wants to know what's the limiting reactant, what are the excess reactants, how many grams of AuOH3 can form, the theoretical yield, so on and so on. So when we're given an amount of this, we're also given an amount of this. This is kind of like saying, hey, I have a cup of flour and I have 3 eggs. How much of this product can I produce? So what I need to do is through stoichiometry, I need to convert this into the product and I need to convert this into the product. So I've got to go grams of this into moles of this, moles of this into moles of this, moles into grams, grams into moles, moles into moles, moles into grams. So we're going through that process 2 times. Then once we have the 2 answers, we can determine which one's the theoretical. So let's go ahead and do that. Clear this out. And these theoretical yield problems, when you have to do it like multiple times, they can like take a little bit for sure. So get comfortable with, you know, practicing one of these problems and it taking you 10 minutes or so, unfortunately. So this first one here, I'm given grams of KAuCl4. So I have 20.00 grams of KAuCl4. I also have 25.00 grams of Na2CO3. We're working towards the AuOH3 product. I have to do that twice. So I'm going to start with the first one. Again, my flow chart for stoichiometry is really always going to be grams into moles, into moles, into grams. So the first step here is to get it from grams of this into moles of this thing. So grams of this KAuCl4 into moles of the KAuCl4. So we need the molar mass of this thing. So molar mass of our KAuCl4 it's a pretty heavy thing. $377.9. Okay. So that gets me out of the grams of this and into the moles of this. Now I need to go from moles of my starting into moles of the product I'm working towards. And this is a 2-to-2 ratio, right? 2 moles of this will produce 2 moles of this. So I'm going to put that in there. 2 moles of the KAuCl4 will produce 2 moles of the AuOH3. All this other stuff we can sort of ignore. We needed it in order to have the balanced equation, but now we can just not really think about it. So last step is to get this from moles into grams. So for every 1 mole of the AuOH3, I have to figure out its mass. Hold on 1 second. This has a mass of 247. 247.98. Okay. I don't know why this pen isn't working for me. AuOH3. So the grams of your initial compound disappear, the moles of your initial compound disappear, the moles of your final compound disappear, and you should just be left with grams of the final one. So we've got to plug that in. So it's going to take 20. We're going to multiply it by 2. We're going to multiply it by 247.98. We're going to divide it by 377.9, and also divide it by that 2. This tells me that I will get 13.12 grams of the AuOH3. So same process as we've been doing thus far, grams to moles to moles to grams. Are we done with the problem? No, we've got to do the same thing, but for this other ingredient. So here I've got to convert grams into moles. So 1 mole of the Na2CO3 weighs 105.98. Then I need to convert from moles of this into moles of the product. So I've got to go back to that relationship. 3 moles of the sodium carbonate produces 2 moles of the gold hydroxide. So it's a 3-to-2. Let's go ahead and put that in. 3 moles of the Na2CO3 will produce 2 moles of the AuOH3. Since we're going to the same product, I can just use that same molar mass for that last step. I don't have to recalculate it. So 1 mole of the gold 3 hydroxide will still weigh that 24.7, or sorry, 247.98 grams. Moles, grams of this cancel. This is a gram. Moles of this cancel, moles of that cancel, and we're left with grams of the product. So plugging that in, we get 25 times 2 times 247.98 divided by 105.98 divided by 3. This gives me 38.997. So really it gives me 40.00 grams of the AuOH3. So this is a smaller mass value and it produces a smaller product value than this one, but that's not always the case, okay? You can't always assume because this is 20 and this is 25 that this will be the limiting reactant. Sometimes it doesn't work out that way if the ratio is really large or different. So in this case, if we're wondering what's the theoretical yield? In theory, what could I produce? Can I produce 40 grams of this? No, I don't have enough of this, right? It's whatever the lower amount is. So this becomes my theoretical yield. What is my limiting reactant? What is holding the reaction back? This is the limiting reactant. What is my excess reactant? It's whatever I have more of, or I'll have stuff left over. So this is the excess. So just like with the recipe, you know, you had to go from eggs into pancakes and flour into pancakes. We're going from one compound into a product, another compound into the same product. So we can compare them, figure out which one's the lower amount, that's the theoretical yield, and then the limiting reactant goes along with that theoretical yield. In this problem, it gives us, it asks you how many grams of the excess reactant reacted. I'm not going to test you all on that, so I'm not going to stress about that. But one thing I do want to let's look at this bottom one here. It says, what is the percent yield if 9.84 grams of AuOH3 is actually produced? So it's giving us an actual amount, 9.848. Let me put that in. So we know that we have 9.848, already forgotten, yeah, grams of the AuOH3. This is the actual yield. It's saying, hey, what's the percent yield? How good were you at running this equation? So remember, percent yield is A over T times 100. It's actual over theoretical times 100. The actual will be given to you, the theoretical may be given to you, or you had to calculate it in the previous step. So for us, our actual is going to be 9.848 grams. What is our theoretical? Let's pop back up here, 13.12 grams. Okay, so we could have produced 13.12 grams, but we didn't. We produced 9.84. Multiply it by 100 as well to get it into percentage, and we'll figure out how good we were at producing this gold hydroxide. So 9.848 divided by 13.12 times 100 gives us 75. 75, and I'm going to give it 2 decimals, 75%. 75, and I'll give it 75.06%. Okay. So that's how that recipe thing translates to an actual stoichiometry problem. You go from grams into moles, moles into moles, moles into grams, compare them, find the lower one. If we're doing percent yield, we take actual over theoretical times 100. Ugh, it's a lot, right? It's a lot of math. We go back to some math for this last chapter here. Let's see. Is there anything else? We do talk about enthalpy here a little bit. I don't want to get into that just yet. Okay. So I think we'll stop there just a little early. We will do another one of these problems. Don't worry. We're going to do another one on Thursday. We'll go through the whole thing. I'll give you 2 amounts. I want you to calculate the product. We'll do all that. All right. And then there'll be one more thing that we're going to layer on. Now, this is a pretty intensive problem. So your next test, don't expect to have like 16 of these, right? You'll probably have 1 of these, maybe 2 tops, because they are quite demanding. Does anybody have any questions on what I did here outside of you want to do another 1 or 2 of them? Because we'll definitely have time to do that. Any questions? Where did those numbers come from? How did that happen? Okay, well, I'll call it for today. If you have any personal questions or I didn't get to an email that you need me to answer right now, please stay around and I will love to help you out. Otherwise, enjoy some of this really nice weather, and I will see you on Wednesday at 9:30 a.m. Bye, guys. Melissa, do you have a question?